Hey, good evening. It's Shelly with Thursday Night Statistics, and the last video I'm going to make for a while is a paired samples t-test and looking at confidence interval and effect size. So like normal, I will start out by sharing my screen with you. And we are going to look at a set of data that we have been using all semester. And this is very busy, so we'll go through it a little bit at a time and see what we can decipher from here. So, um, in looking at this, we are looking at, well, we'll click here. We started with the OG or original combined STAR data for grades 3 through 8 reading STAR test. And we cleaned up this data a little bit to match our research question. And we are now looking at just third and fourth grade data for 2017 and 2018. So my research question starts out with, is there a statistically significant difference in the mean raw score of students taking grade 3 reading STAR in 17-18 and the mean raw score of the same students taking the fourth grade reading STAR in the 18-19 school year? So why would this be important? A more likely test would be students moving from fifth grade elementary school to sixth grade intermediate school because of the jump, whereas fifth grade elementary school is still protected. Normally, fewer teachers and middle school or intermediate school students are turned loose on their own and are making several class switches and have a higher level of responsibility to themselves. But there is reason for looking at the move from third grade to fourth grade as well. In many districts, such as my own, in third grade, students are still self-contained. So they deal with one teacher all day for all of their core subjects. And then in fourth grade, they begin departmentalizing and switching classes. So it's important to look at the effect of having a single teacher all day for your multiple classes versus switching classes and having to become accustomed to multiple teachers, multiple teacher routines for multiple subjects and the like. So that's why I chose that research question. And then the next thing you need to do is pick a test. So I decided to use a paired sample t-test. And I'm going to use that because I want to compare the means of the same participants over 2 points in time, 17-18 as third graders and 18-19 as fourth graders. Next, we must check the assumptions. So assumption number one, that the sample is random. Yes, these students enrolled in this district or were enrolled in this district as third graders. I did not go out and seek them. They would have been enrolled whether I had been involved in the study or not. These same students were enrolled in the same district in fourth grade. So the sample is completely random. The second assumption would be the independence of observations. And we can say, yes, this is true, because each student within this testing group is independent of one another and their test. That means that student A had nothing to do with student B or their test. The population scores are normally distributed. Remember, we can further verify this with a histogram or a box and whisker plot. So then we need to list our hypotheses. And remember, we'll always choose two hypotheses, a null and an alternative. So my null hypothesis says that there is no statistically significant difference in student performance from the 17-18 grade 3 reading test to the 18-19 grade 4 reading test. Conversely, my alternative hypothesis would say that there is a statistically significant difference in student performance from the 17-18 grade 3 reading test to the 18-19 grade 4 reading test. So to establish some data, ran the mean of the 17-18 grade 3 test and came out at 21.16209.476 with a standard deviation of 7.355675423. Did the same calculation for the 18-19 grade 4 mean, which was 22.60349.127 with a standard deviation of 9.19192391. So what does this mean from just a cursory glance? A higher mean in 1819 means that the students scored higher overall. Their average score was higher, but the higher standard deviation means that there's a wider range. So kids overall did better, but there was a bigger spread between the lowest and the highest scores in 4th grade. Of course, we need to set the alpha, which is 0.05, because we're in education, a confidence interval of 95%, which we'll look at further down the road, is completely fine because it's not a life or death matter. So just quickly, I want to go back and take a look at my data set here. I left a student identifier, grades enrolled, so we could see grade 3 and grade 4, the student gender, their ethnicity, and their race. And then I have the raw scores in 1718 and 1819, along with the difference. And to set up the difference column, what you do is look at the difference between the two tests. And it gives you an average, and then you can go to the corner here and pull it down, and it uses the same formula to determine your mean all the way down. That would be your mean average. So, taking a look, along with our hypothesis and our t-test, it's important to notice that yes, it is a pair sampled, but it's also going to be two-tailed and non-directional. So, tying into the distribution of differences, yes, I can look at this column and see that there's differences in testing, but I can look at the standard deviation and the mean and see differences. But when you put it to a box and whisker plot, then you can really see where the data lies. And so we're looking for this to fall in some sort of a normal curve or a normal distribution. And this is a robust assumption with the outliers outside of the whiskers. But we can see that within the whiskers, it's fairly normally distributed. So the next thing we need to do is start calculating some statistics. All right, so calculating statistics. We need to look at 2018, and the population size, or really our sample, is 1,604, as it is in 2019. And all that means is that every student we examined as a 3rd grader in 1718 had a score, or the same students had scores in 1819 as 4th graders. Then we determined our degree of freedom, which was a sample size of 1604 minus 1, which gave us a degree of freedom total of 1603. So 1603 is going to be a critical number that we work with throughout this exercise. We had to determine a t-critical value, and you would get that from going to a t-critical chart, which I have shown you in several videos. It's just a random chart that you can pull off the internet. And what you do is you make sure that you are looking at an alpha of 0.05 for a two-tailed test. There's different alpha sets and one tail or two tails. So it's important to make sure that you get the proper alpha and the proper two-tailed. And you would search down for degrees of freedom. And this is just a partial chart, so it doesn't go very far. It was more just a representative to demonstrate to you what it looks like. But looking at a chart, when you start getting up over the 500 mark into various large numbers like this for your degrees of freedom, you're kind of at an infinity. So there's typically a set number for your critical value. And we're going to use this critical value at 1.960. So next it's time to run the t-test with the paired two samples for means. When we were running the one sample, that's in order to run a two sample test, we had to create a dummy data point. But in this test, we actually have two authentic data points to use for 1718 and 1819. So we can just run the test as we've done before. Then the 1718 test, it showed us there was a mean of 21.1621 and a mean in 1819 of 22.603, etc. If we were to scroll back up to the beginning of this exercise, you would see that these numbers match the numbers that we created from a simple calculation without data analysis. We can see that the variance shows up in the 17-18 test just over 54, and in the 18-19 test, it shows up at almost 85. So again, the means show us a difference, the variance shows us a difference. We're looking at the same number of observations at 1604. We have our Pearson correlation, which would be between -1 and 1. This is obviously on the positive side, which is showing a correlation, a stronger correlation in a positive fashion. So graphically, it would be represented from bottom left-hand corner moving upwards to the right-hand side of a chart. We're using a hypothesized mean difference of 0 because in our null hypothesis, we said there was absolutely no difference in between the means for 17-18 and 18-19. We established our degree of freedom earlier at 1603. So then we come up with some critical numbers. And critical numbers that we're going to look at and use in this test, specifically our t-stat, which was -8.53. And then we want to look at a p-score for the two-tail, which was 3.2 to the -17th power. So that's scientific notation and represents an extremely small number. And then we want to look at our t critical value, which we had established earlier for a two-tail test at 0.05 confidence or 0.05 alpha 95 confidence interval at 1.96. So these are the three big numbers that we are going to work with over the course of the test. So we could highlight them if we wanted to, but for the sake of time, we will highlight one just to quickly show how it's done, or maybe even not, but just notice that we're going to focus on these numbers. So moving down, the next thing I did was pulled a normal distribution curve. Again, this is something you can get off of the internet. So this shows standard deviations from the mean and t-scores and probabilities within the curve. You can see within these two marks right here, the 95% of values right here, this is 68, and then we've got these tails on the end. Important to note about the curve that if it happens here, anywhere in here, our statistical values, we're going to fail to reject the null. That is, we're going to accept the null, stating that there's no difference. And if it falls on either end of these tails, then we are going to reject the null hypothesis, which shows that there is a difference. So, that's a mouthful. These orange lines represent our t-critical value of 1.96 on the positive side and -1.96 on the left-hand side of the mean. So we're looking for something to fall within negative and positive 1.96 if we're going to fail to reject. When we ran that t-stat earlier, we came up with the -8.53. So I drew this thick line over here to show, because if t-scores and values, if we're looking over here, 2, 3, 4, 5, 6, 7, 8.5, our number -8.5 would be this far off of the normal distribution, and this tail is going to be skating that axis. So as we can see, it is way outside of the area, and this tells us that we want to reject our null hypothesis. And then when we had the score earlier of the -3.16 to the 17th power, or to the -17th power rather, that gives us this fractional tiny microscopic number. I wouldn't even know how to pronounce this number. I just know that the 3 starts at the 17th digit to the right of the decimal point, and that number obviously is far less than the 0.05 that we used for our alpha value. So that tells us also that we want to reject the null, because remember, we're only failing to reject if values fall within here. So we learned within this module that on a test like this, we can't use the Cohen's d or the Pearson. So what we must use is a test called eta squared. So to determine eta squared, what we want to do is look at our t-squared value. So we had our t-score of -8.53, and we squared it and came up with -72.8. Then we add the degrees of freedom of 1603 and subtract 1, and this gives us a number of 1529.1268. So our ETA square number is 1529, which is huge. If we think about the mean for our third grade test at 21, and the mean for our fourth grade test at 22, this number, this ETA square number, tells us that there's a huge difference, and this is yet a third way that we can prove statistical significance. So we also have to take these numbers and look at effect size. So to determine our effect size, we're going to do t squared minus the ETA squared, or t squared divided by the ETA squared plus n minus 1. And this gives us this tiny number of 0.04. And given our ETA square value of 0.047, we conclude that there was a small effect, if any. We're looking at a confidence level of 95% or 0.05, shows that it's close in nature to the effect size. So the last couple of things we want to do during this video is some testing for confidence interval set at 95%. Remember, that's an alpha of 0.05. And we're looking for the confidence interval for the difference between population means. So again, we start out with our sample. And that actually should have been 1604. The degrees of freedom was 1603. It was calculated based on that, just a typo on my part. And then we relist from earlier in the table our means for 1718 and 1819. These are the values we pulled. We could pull them from the hand calculations at the top or from when we ran statistical tests midway through. And then we pulled the mean difference of the difference and then the standard deviation of different scores. So we came up with 1.44 and 6.76. Our t-crit value we pulled earlier from that chart at 1.96. So we're going to look at the sums of mean 1 minus mean 2. So we plug in these numbers. And then we're going to look at the standard error of mean differences, to which we came up with 0.168849. So two other formulas we want to look at is the standard error of mean differentiation for difference of scores, otherwise known as SMD. And to calculate SMD, you take the standard deviation divided by the square root of n. So when you plug in these numbers, I came up with 0.1689023. And you'll see that that is statistically significant in a little bit. Then we also want to look at the formula for 95% confidence interval for the difference between population means for a paired sample t-test. And to determine that, we take our mean 1 minus mean 2 plus or minus our t-crit value times the SMD. So when I plug in these numbers, if I take this plus this, I come up with 2.49 and change. If we do the 21 minus 0.3310, we get 20.83. So scientists or researchers, they want the difference in these two values to be tight or narrow or close together, meaning that there's not a statistical significance. But when they're far spread like this, if you were to graph these between 2 and 20, that is a huge range, not tight at all. And that's a large effective size, which means the significance between these two tests is of great importance. So when we take that, we look back at our initial question. And if you remember our initial question, we were looking to see if there was a statistically significant difference between the means or raw scores of third grade testers in 1718 and the same children testing as fourth graders in 1819. And our testing, our effective size, along with all our other testing, tells us that 1, there is a statistically significant difference, and 2, the significance is of great importance. So that may give us further reason to look into the significance of third grade to fourth grade classes. And as campus administrators or district officials, we might want to start looking into third grade and fourth grade classes and comparing scores to see if, situations like this where there's a large difference, if maybe the third graders are self-contained and fourth graders switch classes, it may pan out to be harmful to some and not to others. And then there's other factors we can look at, teacher strength, teacher experience. But this test in general tells us with these levels and this range of significance that it is worth digging into further. Thank you for joining me. I'm going to stop my share, and I appreciate you being a part of my video, and have a great night. Until next time.